So, hello everybody. My name is Rainer Beusel, and today I'm going to present our framework for mobile voice over IP steganography. First of all, I want to introduce my colleague, and it's not Markus Nutziger, I'm sorry, this is Jürgen Wurzer, and he is also a member of our developer team. And our developer team consists of 3 people, and it's including Markus Nutziger as well. Before I start with the actual topic, I want to show you or to introduce ourselves to you. And so all 3 of us developers studied telecommunications and media at the St. Pölten University of Applied Sciences, and we are employed at the Institute for IT Security Research in the same university, and we're working in the project StegIT2, which is about this framework I'm presenting together with my colleague today. And we're also involved with the building up of a competence center for digital forensics. So if you're interested in these topics, don't hesitate, just talk to me after the talk. We can maybe have some interesting conversations. I also wanted to mention that at our university we also have research projects in the field of biometry. So I'm not really involved in these fields, but if you need some contact information for other people who are involved in this field, just ask me, no problem. The StegIT project, I also wanted to mention that the StegIT project is funded by the Austrian Research Promotion Agency. So it's a funded project which has been running for now more than 1.5 years. So it's more about presenting the results of this whole project. Before it's getting technically, I wanted to introduce some terminology in the field of steganography. So I think almost all of you have heard of cryptography, which is related to hiding information. So it's the study and practice of hiding information and the protection of secret data. But it's important to mention that in this field, the data transfer or the transfer of data is obvious. I also wanted to mention the term cryptology, and this involves both cryptography as well as cryptanalysis, which is about finding out if the mechanisms which have been implemented in cryptography are secure. But today we talk about steganography, and in this field the existence of secret information is not known or shouldn't be known. That's the most important fact or contrast to cryptography. So in steganography we hide secret information in innocuous messages. It seems unsuspicious if we transfer something. So this is a world map of internet filtering, and it shows the countries in which internet filtering or the filtering of content or applications in this field is performed. And this map shows also the fields in which you can apply steganography. I want to mention some of these countries. I think most of you have heard of China with its great firewall, and also important is the fact that North Korea also performs some internet filtering. So in North Korea, for example, the usage of the internet is restricted to just a few people. It can be compared to South Korea, but in South Korea, internet access is allowed, but there is lots of filtering performed when it comes to information about North Korea. So this can be understood if you think of the news of the last few days that there is more or less war between North and South Korea. So another important country in this field is Iran. And in Iran, there's lots of filtering regarding information about women's rights, democracy, or pornography as well. So these are mainly the countries in which steganography could be used to communicate with other countries with less restrictions. So, before I present the framework, I want to give you a brief introduction what steganography actually is. So we have a secret message which is embedded into a so-called cover, which can be image data, it can be video data, or as in our case, it can be auditive information as well. And this step is performed a so-called encoder. And after embedding the secret information into the cover, we get the so-called Stego object. And this Stego object should look like the cover message for a person which is not involved directly into this communication. And when we have the Stego object, we transfer it using a so-called communications channel to the decoder, which extracts the secret message for the destination. There's also the original cover mentioned because there are some algorithms which rely on the original cover to extract the secret information. And as well, there can be some key involved. So there are algorithms which consider using a key for even more secure communication. So you can combine steganography with cryptology or cryptography. So let's get technical. I want to introduce our framework. So our framework is actually what we see here in the box with the two words embedding and extraction. So if there is Alice, Alice has a computer with a sound card, and we take the auditive information from the sound card and we can embed information as we had it in our previous slide. It's the encoder, and so we get the Stego object. And on the other side, the framework is also able to receive a Stego object from another framework, so it's the same framework, and it extracts the information and it brings the so-called cover medium back to Alice. So Alice is on the one side, it's a producer of the cover medium, and on the other side, she is a consumer of a Stego object from the other side. And we also implemented a GUI, a graphical user interface, which can be used to interact with this whole framework. You will see more of this when we do a live presentation. We have been preparing some speakers to give you an idea how it sounds if we embed information in other auditive information, and you will also see the GUI which you can use to interact with this framework. So, let's talk about a specific scenario. And in this scenario, we have two voice over IP clients. There's one on the left and one on the right. And we have two routers which are used to connect these voice over IP clients with each other through, for example, the internet. This slide shows you what actually happens. So in the routers, we can embed information. Let's say we can embed information in the cover medium provided by the left voice over IP client. And we can extract information which comes as a Stego object from the voice over IP client on the right side through the right router. And on the other router, let's say the router on the right, it's exactly the other way around. So we can also use the same scenario for GSM calls. So it has to be mentioned that in GSM, the auditive information is compressed radically. So it's really lots of information loss involved. So we need to develop or to implement a very secure or robust algorithm. And we did it. So there is specific slides to this topic as well. And the setup is almost the same as with the routers on the slides before. Just we have two mobile phones which communicate to each other over a provider's network. And this provider's network is not displayed on this slide. So please don't be confused about that. Yeah, before we directly go into the architecture of our framework, I want to show you this in a specific process. So first of all, we brainstormed which components we actually need to perform a steganographic data transfer. So the most important, I think, is the unification of secret data and the cover medium. It's the embedding engine, like we call it. You also need some additional information which you append to the information which you want to transfer. So we have a protocol for the data flow handling, and in this field we also have some techniques which take care for the integrity of data as well as the segmentation of data. So if we want to transfer data, we need to say, okay, this is a specific packet. Here it begins, here it ends, so that we can perform some error checking, so that we can assure that the information that we transport is correct. Then we also need the management for component instantiation, so this is something from the object-oriented field. And we also need interfaces for third-party software. So this could be interfaces to voice over IP phones, such as Ikiga, let's say. This is an open source phone. Or we also need interfaces to the routing process of an operating system if we want to embed data into voice over IP calls, or it means that we need an interface for a sound card in case we want to embed information into a GSM call, for example. It's important to mention that we need a sound card interface for the GSM embedding because most GSM phones don't support the direct manipulation of samples. So we just have the auditive or the audio analog interface. So now that we have the components, we can arrange them in a layered model. And we proposed a 6-layered model for steganographic communications in auditive media. So first of all, on layer number 6, which is on the top, we have the secret data. And the secret data can be, for example, a passphrase, or it can be a secret key for some encryption. And this data is usually available in bytes. So when we have the information we want to transfer, the secret data, we need to add some protocol information. And we decided that after adding the protocol information, meaning this packet headers, packet begin, end, we have bits. We represent the data in bits. So it's a bit-based protocol. And after we have the bits extended with the protocol information, we introduced the so-called presentation layer, which is not always required, but at least required for some techniques like spread spectrum, which I will introduce later on as well. So the main thing for the presentation layer is to represent bits we want to embed with so-called chips. So it means spreading bits into chips. After that, we can actually uniform, or we can bring the cover medium together with the secret information, the so-called embedding layer. And because of embedding the secret information in auditive information, we have samples. So after embedding, after unifying the secret message with the carrier or the carrier object, we get samples. And some of these techniques also require synchronization. So they need to know when a specific data transfer starts or ends. And after performing the synchronization, there is the actual transmission going on, meaning that we hand over the samples, the modified samples, to the transportation medium, which can be RTP packets in case of voice over IP, or just samples which are given to the sound card. So now that we have brainstormed the components, brought them into a layered model, we can actually talk about software architecture. And instead of mentioning all the components you can see, we decided to just show you two different things. So on the lower part, we have the so-called I/O part. And this I/O part is called by the so-called main procedure. and it is used to get the data from the operating system, let's say from a sound card or from a network interface. And then if data has been read from such a device, it's handed over to the blue box on the top, which represents the whole embedding process. After modifying the data, which means embedding, or the embedding actually, or if data has been extracted, we give it back to the I/O part, meaning in case of networking, we allow the networking subsystem, or we tell the networking subsystem to forward the modified packet now. Yeah. So in the previous slide, there was the main procedure which was reading data from the I/O, from the I/Os, and handed it over to the embedding algorithms. And on this slide, we just wanted to give you a short flow chart showing you the logics behind the main procedure. So first of all, we have the start, meaning starting the whole framework, the main procedure, and it's an endless loop actually. And in this endless loop, we start by reading information from the I/Os, meaning intercepting a network packet or some information from a sound card, and then forwarding it to the embedding algorithm, which is represented here in this action decision box. And after the embedding or the extraction, so the framework needs to detect if there's information which needs to be embedded or extracted, we give the information back to the so-called write method, which places the modified data back on the network bus or onto the sound card. Another important thing on this slide is you can see that the extraction from Stego objects is an asynchronous process. This can be understood if you think of techniques which rely on the analog representation of data. If you really look at the audio signal, techniques which rely on the audio signal, you need to buffer a certain sequence. And if the extraction takes too long to investigate this audio signal, there could be a delay, and the receiver of this should be innocuous messages could recognize that there is a delay, there's some processing going on in behind. So that's why I decided to copy this packet buffer or this samples buffer and let it process by a specific thread. So on this slide, I wanted to dive into the actual implemented algorithms. So we have two kinds of algorithms. So the one is working in the so-called spatial domain, meaning operating on the digital information itself, or in other words, meaning that we directly modify the samples. And on the other side, we have approaches which work in the so-called transform domain, meaning they regard the actual audio signal. So they are working on the analog representation actually. And in this field, we implemented the so-called echo hiding, which is representing hidden information in kind of an echo, and the delay of the echo signal represents the information, meaning being a 0 or being a 1 for digital data. Then we implemented the so-called spread spectrum, which represents hidden information like similar to noise. And this is what we wanted to show you actually, just to an idea. And then we also implemented phase coding. Best of all these three techniques, it was the spread spectrum approach. So I also wanted to show you what happens to the samples. So as mentioned on the slides before, there is approaches which work in the spatial domain and in the transform domain, and approaches that work in the spatial domain can work on samples directly. So they just take the stream of samples of the auditive information and modify single bits, which is the case for the least significant bit hiding, which was also mentioned on the slide before. So you just modify the least significant part of samples so that at least the human senses cannot hear it. So, but it's also important to mention that this approaches only work for codecs that don't mind if you change something of the encoded samples. Meaning, in our case, we were only using the G711 codec. So if you take some codecs like G.729, this is not going to work because it's a more complex encoding technique. So if we want to work in the so-called transform domain, we need to get a representation of the analog signal. And this means that we need to, you can see this on the right path of this flowchart, that we need to decode the signal first before we process it, meaning embedding information or extracting information. And after that, we encode it again. This is two important things to mention. This takes lots of computational power, and on the other side, you have a quality loss, sure. So, I also wanted to mention something of some facts about the embedding architecture as well. And it consists of 3 parts. So on the lower part, you don't need to see what's in the boxes, but it's just in the red box you can see that we have different embedding algorithms implemented. And these embedding techniques require data to be embedded. So we have the green box on the top, means it represents the data which is embedded into the cover medium using the embedding algorithms on the lower end. So the blue box in the middle is also important because it shows you that you have the choice of using protocol data or not. So you don't necessarily need to use protocol data before the transmission. But if you think of packet loss or other noise which can be added on the communications channel, then you would regard this and can decide this in the configuration of our framework. So, now that we've talked about the framework itself, I'm going to talk a little bit about the implementation. So, the first implementation of this whole framework has been performed on commodity PC hardware, meaning it has been performed on 32 and 64-bit Intel processors. But shortly afterwards, we tried to port it to the so-called MIPSL platform. And as you might know, the MIPSL platform can be found on home routers, like the Asus WL500G Premium version 1. This router is based on the Broadcom chip, Broadcom 4704, and it's pretty cheap. It's 50 to 70 euros now, I would say. So to port our framework to this hardware, we used a modified OpenWRT SDK. This OpenWRT, it's an alternative alternative firmware for home routers or other devices which are usually embedded or small. I'm talking about the modifications to the OpenWRT SDK soon. And this gave us the proof that we should consider porting to other platforms as well, meaning platforms that provide either a routing interface or an audio interface. Let's talk about the OpenWRT SDK adaptations. So OpenWRT, the kernel for OpenWRT is not configured to support the so-called NFQ. The NFQ is used for the routing process, meaning that the NFQ allows you to process certain packets you want to process in user space. So you don't need to write the kernel driver to intercept network traffic and modify it. So it's comparably simple. And one advantage is that if you use the NFQ, it doesn't mean you break your system or you just shoot it by writing an erroneous kernel driver. But on the other side, you have the problem of performance. it takes more time for the computer to process it. Then this was the most important thing, because NFQ, it's not supported by OpenWRT, and you have to modify some makefiles to support it. Then we added some additional packages just such as FFTW, meaning you can do some fast Fourier analysis, and some other libraries, GSL, the GNU Scientific Library, giving you some mathematical algorithms as well. So as soon as you have created your OpenWRT SDK, you have to create a firmware image for the router, and this firmware image required the customization of firewall settings, because you had to tell it to use the so-called NFQ target for being able to process packages in user space. And we also had to customize the start scripts of this Linux, which OpenWRT actually implements. To be honest, this embedded router was too slow, at least for the more advanced algorithms, such as spread spectrum or echo hiding. There were big delays on the voice VoIP calls, but it worked good for, let's say, for LSB, for the least significant bit hiding, in which you just directly modify the samples without any encoding or decoding. I also wanted to mention the implementation of this framework, or the porting of this framework to mobile or smartphones. And there is actually, to be honest, it's nothing implemented. We're just doing some research if it's possible on what we need to do. So actually, we only thought of using Linux-based smartphones. And in this case, we could think of Android phones to be used. And the NDK, which is available for the Android phones, it's the developer kit, the native developer kit. And this native developer kit also provides C++ compiler. So our source code was mainly programmed in C++, and using the NDK, you could, I assume it's not too difficult to port it to the Android platform. Then we thought of two scenarios we could implement on mobile phones. So the first one should be more simple than the other one. So voice over IP means that we need to adapt, modify the network stack of the smartphone. And as Android is a Linux-based distribution, it should be possible to use the NFQ here as well. And on the other side, we are doing some research if it's possible to modify the voice data of this mobile phone directly, which is better because you could then use a provider's network to communicate securely then. Okay, so it should also be mentioned that another project goal of Steg IT2 is that we implemented some algorithms for the prevention of steganography. We did this to prove that our approaches and techniques are robust enough. And we took 4 different approaches. The first one is assuming the most simple one. We were adding noise, so just some random patterns. So then we implemented the jitter, meaning we were playing around with the delay in which we waited for packets before we forwarded them. Then we also were working with frequency shifting, meaning that we transposed the music a little, or the auditive signal a little bit, meaning it's semitones. This was actually the most effective one. So almost no embedding algorithm could survive if you modified the Steg object with frequency shifting. And then we also used signal cancelling, meaning that we just set the frames or the auditive samples to 0, meaning representing 0 hertz frequency. Before we do the live demonstration, I wanted to give you an overview of the setup, the demonstration setup. So we are using this laptop here, the presentation laptop, directly. And on this laptop, we installed 2 virtual machines. One is called Alice, and the other one is called Bob. And on both of these virtual machines, there is a voice over IP client, and we decided to use Ekiga, which is an open source client. And we also have the framework, which is abbreviated with FW here. And connected to this framework is the GUI, the graphical user interface. So we have this for 2 computers, and between them is the actual host, meaning this physical laptop here. And on this laptop here, there's also the framework running in defense mode, meaning that if Bob transmits information, let's say the cover provides the cover medium and the stake object for Alice, we add some noise, or we can add some noise. You will see this in the graphical user interface we implemented. And depending on how strong we set the levels for the noise we add, you will see how good the embedding algorithm survives. Okay, so I will hand over to my colleague Jürgen now, and he will show you this in a virtual machine.
Okay, we have 2 virtual machines. Here is Alice and Bob. And we also have the defense machine, which has 2 virtual interfaces to the virtual machines, VNet 1 and VNet 2. Yes. Okay, here is Alice, the virtual machine Alice, and we can see we have a start script, which here we start the framework with some parameters. And before we must set some IP tables rules to get the RTP packets.
So you will see we have 2 IP tables rules, and these IP tables rules are added to the output chain and to the input chain. So on the output chain, we perform the embedding, and on the input chain, we perform the extraction. You will see to intercept RTP packets, which are used in voice over IP phones, we decided to intercept only UDP packets with a destination port range from 1024 and up, because usually it's user-space programs which perform the voice over IP call, and with a source port range from 1024 and up as well. And as a target for these rules, we decide to use the NFQ, meaning bringing these packets to user space, and we decide to only use the queue number 1. Newer implementations of the NFQ support different queue numbers, so you can decide to start more than just 1 instance of a framework. Yeah, and then, as mentioned before by my colleague, we start StegIT2, which means it's the name of the binary implementing the framework, and it's called with lots of parameters which are required for the auditive interception.
Okay. Additionally, we have a config file which includes the embedding parameters, the Stego key, and so on. Yes, now we start the framework. And the framework waits for the GUT. Okay, the same must be done at Bob. Okay, now we can start the iPhone client. Achso, genau.
It's important to say we're not working on a live voice over IP phone. Instead of that, we decided to take a WAV file which is fed into the voice over IP phone, a Giga in this case, and this voice phone produces the RTP packets then, which are after that intercepted by our framework. So don't be scared, it's just a call we recorded before.
Okay. Okay, now we call Bob from Alice.
Ja, bitte. Du hörst mir, nicht ich.
Okay, this is now we have the call and we can use the GUI to communicate with Bob. Okay, we just type test. And we have a bitrate about 3 bits per second. That's not really much. Yes. And here we can see the qualities from extraction.
So, as you can see, there are numbers between minus and plus 1. And all numbers above 0, meaning bigger than 0, state there is a bit, a true bit received. And if there is a number below 0, meaning being smaller than 0, we indicate that there is a false bit received. You can also see the number indicates the quality in which we received the bit. This will change as soon as we turn on the defense, meaning adding some noise to the samples in real time.
Okay, now we can see the layers from the protocols, and the stream layer is something like a mini TCP version which guarantees the transmission. And here we see that here comes the message hello, and it's printed here. And on Bob, here's the same. And now I can show the bit quality when I go to the defense and we add some noise. Okay, now we add some noises. Yeah, then. Okay. Here we can see the bit quality is very low, but it also works. The
WAV file is looping over again. So.
Now we can see the qualities not by 1 or -1, but it also works. It had 50%. And the average.
If there is information lost, we have the protocol information which requests the information to be transferred steganographically. Okay. Okay. presentation. So, let's go back to the presentation. Before we finish our presentation, I wanted to give some outlook, some ideas we had regarding our framework. It was just brainstorming, and we mainly thought of using video streams for steganographic data transfer. Video streams offer a way higher transfer rate, so you have much more information where you can embed information, or it can be generally said, if you embed information into images, image information or videos, you have much more space. Then a Windows port could be nice, so in case you use Windows, and it's lots of people out there using Windows, as you might know, there's a broader range of people who could use this program. Then we also wanted to have a better usability. You could see our terminals, which we use to see the quality and such things, but we want to make a better user interface as well. So as well, data throughput should be improved. As mentioned before by my colleague Jürgen, we only managed to transfer 3 bits a second, meaning that we only can transfer key material or, let's say, passphrases or only short sequences of data. Then we also want to port this whole thing to smaller devices, as mentioned before, smartphones or wiretaps, for example. And another important thing is, or would be, steganographic loaders, meaning if you have a USB stick or if you have a router with you traveling to one of the countries mentioned before on this world map, it could be at least suspicious for them that you have something like that in your luggage. So, at the end, I just want to say thank you for your attention, and if you have any questions, just ask.
So, any questions?
Does it work over codecs too? So are you inserting in the audio part or just in using bits in the GSM 711 or something?
Both, actually. We started by modifying the coded values directly, meaning we just modified the digital representation of the analog signal. And on the other side, we can also work on the auditive information itself, meaning the audio signals. So we decode it and then encode it again.
So you're using something like a modem to insert a sub-audio tone or something like that?
No, actually not. We're just really taking the audio stream, meaning the RTP packets which come from my voice over IP phone, for example.
And if these are modified, the codec will have glitches, or these are very audible if you're modifying values when using a codec, aren't they?
Exactly. So if we modify samples of coded values, let's say of something which has been encoded using the G729 codec, you really have a problem because it's just destroyed the whole information. You will immediately recognize it. But if you take simpler codecs like G711, you won't really recognize it, at least with your eyes. If you use a computer to analyze the modified information, or at least the Steg object, because you don't have the original object often, you will still, let's say, easily find it.
So in G711 is just no codec, it's just the raw values from the...
Actually, yes, it's performing some A and mu law compression, meaning putting 16-bit samples into 8 bits, but there's nothing more than that.
But that means the steganography is readily detectable by using audio analysis techniques.
So for the more complex algorithms, it's not easy, because there are so many parameters involved in modifying this information you want to hide that you won't easily find it.
So it's seen as if it's if there is noise.
It's like noise, exactly. Okay. It looks like noise for you.
Thank you.
Any other questions?
is it possible to, or how hard is it to detect if two parties are using steganography with your implementation, given the fact they have your software at hand?
I can say it depends only on the key material. So the algorithms are pretty secure. We concentrated to implement Kerckhoffs's principle, meaning that the whole security only relies on the key material. And these approaches have been implemented by some other institutes around the world as well. And so there's lots of research in this field, and I think it's secure as other well-known things like HTTPS, for example, which is used in another field, but it's also an algorithm.
Have you made any calculations how much more data you could transmit with video?
So this depends on the approach or technique you use. But if you think about LSB analysis and you just take a bitmap file and you just use the very last bit of each pixel's color channel, meaning 3 bits per pixel, this gives you a data range of about 10% of the whole image, meaning if you have a 2 megabyte image, you can hide about 200 kilobytes. But this is pretty unsecure because LSB is, you can easily detect it. There's no transformation in another room, and there's not many parameters involved in the whole thing. But it's ways higher up just because it's almost, you can use the same techniques actually. It looks different because it's visual information, but you have so much more information to just represent something. So representing one minute of auditive information with a good codec just needs, I don't know, a few kilobytes or just something between a few kilobytes and 100 kilobytes per second. But if you take one single image in the size of a digital camera, you have several megabytes at hand where you can hide information. That's the actual fact about the whole thing.
So, any more questions? No?
This is all data hidden in the audio data itself. Have you looked at adding data into zip headers themselves? For example, tag values, session IDs, whatever, and or use the control channel for the RTP, where the one side gives the other side statistics on the quality of packets received. Because I think there should be some ways to use that channel for some other data exchange.
That's a good question. Thanks for asking. So yes, we thought about this because we had to do some state-of-the-art research before we started our project. Because if you want to get your project funded, you need to write some application and you have to prove the state-of-the-art. And when we did the state-of-the-art research, we found out that there are people out there doing this. So meaning looking at the zip headers, for example. I think